Hello and welcome. In this video series, we're going to get into the ideas behind logic, propositions, and being able to really analyze arguments or analyze statements and describe whether those are logically valid or not. So this deals with things like Boolean algebra. We'll get into the notion of truth tables and working with Boolean logic. For the most part, our approach to logic in this class will be geared around Boolean logic. And the reason for that is because oftentimes we want to make justification or prove some sort of theorem. And in order to do so, we have to have enough logical constructs in place to do that. So here we'll just introduce some of the key features of logic and propositions and learning how to analyze statements. So first of all, a proposition is a declarative statement that is either true or false. Whether it's true or false, though, it is not important in terms of telling whether it's a proposition. If you can either say that the statement is true or false, it is in its own right a proposition. So which of the following are propositions, true or false? I am a human being. Well, that's either true or false, and for each creature that might vary, but in general, that can either be a true or false statement, therefore it is a proposition. Am I a human being? Well, I don't know. That's not a declarative statement. That therefore a question can either be true or false. The answer to a question can either be true or false, but not the question itself. X plus 1 equals 2. Sure, well, depending on what X is, this is either a true or false statement. Therefore, yes, it is a proposition. Read this carefully. Oh, wait a minute. That cannot be a true or false statement. I read this carefully could be a true or false statement, but read this carefully is really just a command. So that is neither true nor is it false. So in order to wrap structure around logic, we typically use variables to encapsulate a proposition. For example, in the statement, I am a human being, we're just going to replace that entire sentence with the letter H. Therefore, when you see the letter H, that stands for I am a human being. The reason we want this is we often want to take a more complex statement and turn it into symbolic logic. It's much easier to analyze a sentence or a paragraph that has a lot of logic loaded into it by using logical symbols and to analyze it with such things as truth tables. So look at this statement. If the return value of the function is true, or there is an exception thrown and no traceback, then either the main loop will preemptively terminate or a conditional statement will execute the alternative subloop. Well, on first look, you may be a little bit confused by what that statement is really saying, but if we were to impose some symbolic logic, it might make a whole lot more sense, and we could analyze it in a very mathematical way. So this is not unlike something you might encounter in coding logic, where you need to take something like this and build it into code. However, it may be a bit tricky to understand what this is really saying and what actions may or may not happen. We would prefer to write this statement as something like this. So I won't go through the details of what these symbols are right now, but this breaks up this complex or compound statement into a series of simple statements. So actually the letter A stands for the return value of the function is true. B is there is an exception thrown. C is no traceback. This little V operator, that's actually the word or. So when you connect two simple statements with a disjunction, we'll talk more about this soon, then you can actually take a series of simple statements and combine them to form that compound statement that you're interested in. At first sight, this may not be something that looks fun to analyze, but it allows for the construction of a truth table, which we will soon introduce. So as there are statements, it's important to be able to talk about the negation of a statement. So the negation of a proposition, we'll call that proposition P, is denoted with this little like sideways backwards L, and that is read as it is not the case that P, or you could say not P. Now I'm okay with you using a similar statement. I know some people have seen this before for P not, a P with a little prime above it. Some people maybe have even seen a P with a bar over it to say P not. These are all okay, but logic often uses this L symbol to denote not. But you can use whichever one you want, just be clear about it. So for each of these, write the statement that represents the negation for each of the following. I am a human being. Well, what is the negation to say it is not the case that I am a human being? Well, to say that it is not the case, we don't want to just say it like that because it is not the case that I am a human being just sounds funny. It makes more intuitive sense to say I am not a human being. Okay, what is the negation of I will not go to class tomorrow? Well, we could again say it is not the case that I will not go to class tomorrow. But what does that really mean? So this in itself is kind of already the negation of the statement I will go to class tomorrow. So we could say I will not go to class tomorrow. But that really means that if I won't not go to class, then that means I will go to class. I know that sounds kind of funny, but it makes more intuitive sense to just say the kind of the opposite of this, if you will. I will go to class tomorrow. And what about the statement x squared minus 3 equals 13? Well, if we first of all start off by writing it is not the case that x squared minus 3 equals 13, then what does that mean, that x squared minus 3 does not equal 13? Oh, wait a minute. That means precisely x squared minus 3 does not equal 13. So if it's not equal to 13, if the square of x minus 3 is not equal to 13, then this can imply one of two things. It could be that x squared minus 3 is less than 13, x squared minus 3 is less than 13, or x squared minus 3 is bigger than 13. So that's the only way for something to not be equal to something, is it has to be either smaller than or greater than it. Okay, y is greater than or equal to x. Well, let's think about this on a number line. If y is greater than or equal to x, and this is x right here, and x, currently the statement says y is greater than or equal to that, well, the negation of that would say y is, it is not the case. It is not the case that x, or that y is greater than or equal to x. So what would be the negation of that? Well, if it's not greater than or equal to x, that means the only other possibility is that that y is less than x. And this is just a parenthesis to indicate that it cannot be equal to x, but it can be less than x. So if y is not bigger than or equal to x, that means y is less than x. That's the only other possibility. Okay, y is not equal to x. Okay, so it is not the case that y is not equal to x. Well, okay, so if it is not the case that y is not equal to x, y is not equal to x, and so that really means that y is equal to x, would be our final statement there. Final statement here was this guy, and our final statement here was this guy. Or you could, in this second bullet point, you could have said this in lieu of x squared minus 3 is not equal to 13, but this was just a little bit more compact. So that's dealing with negations, and negations are going to become incredibly important because sometimes when we justify a statement or we want to prove something, talking about negations in something called contrapositive will be much more helpful. So given two statements, P and Q, let's define something on those statements. So P and Q are actually simple statements. And all we mean by simple statements is that there's no and, there's no or, it's just a basic sentence. Like, I am a human being is a simple statement. I will not go to class tomorrow is a simple statement. But if I said, I am a human being and I will not go to class tomorrow, that is not a simple statement because the and is a conjunction. It conjoins those two statements together. So we want things to be simple statements because they're far easier to analyze. So if we have two simple statements, P and Q, the conjunction, so think conjoined twins that are joined together, the conjunction of these statements denoted P with an upside down VQ, that's read as P and Q. The conjunction of these statements is P and Q, is the proposition P and Q, and is only true whenever both propositions are true. We can represent such statements using a truth table to see when the conjunction is true. Okay, so let's first of all start off with looking at P and Q and figuring out what the possibilities are for P and Q. So this is often one of those things that when we look at the truth values of P and Q, now P and Q we've defined as propositions, and propositions are either true or false. So if I first start off building just a little tree diagram to see this for P and Q, so we can say that P could either be true or false. And actually, instead of doing true or false, I'm going to do false and true. That's the same thing, but P could either be true or false. So this is statement P. And then if P is false, then Q could still either be false or true. If P is true, Q could still be false or true. These are independent statements. And so we can see in our truth table that P and Q could be false, 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 true, true, false, or true, true. So those are the different values that we're going to list in our table. And if you notice that the innermost statement, if you alternate false, true, and then you double the number of falses, false, false, true, true, and then if you had another column, another statement, you'd have 4 falses and then 4 trues. So the statement P and Q will only be true if both of your input statements are true. So in other words, if P and Q are both false, then the statement P and Q will be false. If any one of these is false, P and Q will be false. An and is only true when both of the simple statements are true surrounding it. So that is the key situation here, that an and statement is only true when both of the propositions are true as well. So with that said, let's look at an example. Find the conjunction of the proposition P and Q, where P is the proposition Rebecca's PC has more than 16 gigabytes free hard disk space, and Q is the proposition the processor in Rebecca's PC runs faster than 1 gigahertz. So the conjunction of these is just going to be that Rebecca's PC has more than 16 gigabytes free hard disk space, and the processor in Rebecca's PC runs faster than 1 gigahertz. Okay, so this would only be a true statement. In other words, you would not call me a liar if I told you Rebecca's PC has more than 16 gigabytes of free hard disk space and the processor runs faster than 1 gigahertz. The only way in which you would call me a liar is if both of those things weren't true. So if you think about our truth table back up here, you can think about the situations that result in a false as being lies. So if I had an and statement and either of the two simple propositions were false, then you could call me a liar. Like if I said, I will post these notes and I will post the video, but I don't post the notes, but I do post the video, then you can call me out as saying, hey, you said you would do both of these things, but you didn't. So the only situation in which an and statement is true is if both of the propositions in the conjunction are true as well. The disjunction of P and Q is denoted with a right side up V, and this is really the statement P or Q. This statement is an inclusive or, meaning that by virtue of the English language, the outcome P or Q is true whenever either statements or both statements are true. So in our truth table, we wrote false, true, to look at all the combinations of how P and Q could be paired together. Well, if both of the input statements are false, then it is not true that one or the other, right? So in other words, if I said, I will clean my room or I will go to the store, if I did none of those things, then you'd call me out as a liar. But if I said, I will clean my room and I will go, or I will go to the store, and I only go to the store, but I don't clean my room, that's a true statement because I use the word or. And same thing here. If I did go to the store, but I did clean my room, but I didn't go to the store, and I use the word or between those, then that would be a true statement. And also, this is an inclusive or statement, meaning that if I've done both of those things, that you would still call me a truth teller. So it's kind of like an and statement. It's true when both are true, but it's also true when just one or the other is true. Let's try that again. So that's an inclusive or. Usually we don't talk a lot about exclusive ors unless the context just naturally dictates that it only makes sense for it to be an exclusive or. Okay, under what conditions can a student take a class that has the following requirement? Students who have taken calculus or computer science can take this class. So that would mean that I've taken, the first situation would be calc, but not computer science. So maybe I took calculus, but I did not take computer science. Because this is a disjunction, as long as I've done at least one of these two things. So another way to say this is at least one of PQ. Another way I could have satisfied these requirements is if I've taken computer science, but not calc. And they certainly won't say, well, you've taken both, so you can't take the class. If I've taken both of those, I've definitely satisfied the requirements as well. So under any of these three circumstances, I can take the class that this is a prerequisite for. Now there is a definition for the exclusive or of P and Q, denoted P with a plus sign circled, is a statement that is true when exactly one of the statements is true. Exactly one, meaning if it's an exclusive or, so it can't be both. So for example, a situation where you might see this is, let's say you tell a child, you can have chocolate. That's not what I want. We can say you can have chocolate or a bowl of ice cream. Well, if we're telling this to a child, usually we mean this as an exclusive or, right? If they said, well, I'll take both because by definition, or means one, the other, both. But really the way the parent meant this is to say, you can have one, the other, but not both. And so you can see in this table that the only outcome for true is when just one or the other is true. But if both of them are, if both of those statements are true, the exclusive or is a false statement. So if the child said, I want both, the parent would say, no way, you're not getting it. Okay, so but now we often want to combine these. So we have conjunction, disjunction. Those are the most common ones when we're dealing with ands and ors. We also have something called a conditional statement. Conditional statement is one of the form P, and then there's an arrow pointing to Q, and this reads, if P, then Q. So this is kind of like an if statement when you're dealing with computer programming. The statement must be true whenever the condition P happens, and the conclusion follows. So whenever P happens, we're saying then Q. Q is guaranteed to happen after that. It is much like an if-then statement in programming. However, the only time this type of propositional statement is false is when the condition happens, but the conclusion does not follow. So, for example, before we start to look at the truth table of this, let's consider the following statement. If I am elected, then I will lower taxes. So if we reason through this and we say, what is this politician really saying? The politician is telling us that if he or she is elected, voters would expect this politician to lower taxes, right? So suppose the person is elected, they lower taxes, they've told the truth. Furthermore, if the politician is not elected, then voters will not have any expectation that this person will lower taxes, although the person may still have sufficient influence to cause those in power to lower taxes. So if we think about this statement right here as P, and we think about this as Q, and we look at when we would expect this to be, this P implies Q to be, or if P then Q to be true. So if the condition happens, he's elected, and he does lower taxes, then he has told the truth. But if he is not reelected, he still lowers the taxes. The statement itself is still a true statement. It doesn't say, I will only lower taxes if I am elected. It just says, okay, I promise you that if you elect me, I will lower taxes. But there's nothing stopping that person from lowering taxes anyway. And now if, let's say the politician isn't elected and he doesn't lower taxes, he still told the truth because he didn't guarantee he would lower taxes. He didn't say anything about lowering taxes if he wasn't elected. But so we just say that statement is true. So the only time it's false is if, let's say, he is reelected, or he is elected, but he doesn't lower taxes. He has told a bold-faced lie. And in that case, we would say that's the only circumstance in which an if-then statement is false. So here's the truth table for it. So it is only when the politician is elected but does not lower taxes that voters can say that the politician has broken the campaign pledge. This last scenario corresponds to the case when P is true but Q is false in the if P then Q statement. So here's the truth table for it. So we can see that it's always true. The only time it's false is whenever P happens, the condition happens, but the conclusion doesn't happen, then that if-then statement is not working properly. It's a false statement. Now, there are lots of ways an if P then Q can show up. So the most common is the first one here. You can see if P then Q. Some people will, so I'll just kind of highlight the most common ones that you'll see. If P then Q. P implies Q. So that's the same thing. If P comma Q, P is sufficient for Q. Okay, so P is sufficient for Q means that the way you can think about this is that if P happens, that is sufficient enough for Q to happen. Another way you could say that same thing is a sufficient condition for Q is P. So the condition P happening is sufficient for Q to take place. Q if P, that's just the same thing, just saying if P then Q. Q whenever P. Q when P. Q is necessary for P. That's kind of a weirder one, but it means it's necessary. It necessarily happens when P takes place. A necessary condition for P is Q. So if P does happen, Q happens. Q follows from P. Q unless P doesn't happen. So some of these are less common ones, but just so that you're aware of other statements, you can always reference this. Example 3, let P be the statement Maria learns discrete mathematics, and Q the statement Maria will find a good job. Express the statement P implies Q as a statement in English, then reason through why it is only a false statement when P occurs, but Q does not follow. So we would say, if Maria learns discrete mathematics, let's abbreviate that, then Maria will find a good job. Okay, so if, say, Maria doesn't learn discrete math, does that mean she won't get a good job? Probably not. So the only time, if I said, Maria, if you learn discrete mathematics, then you will find a good job, that doesn't mean the only situation that she'll find a good job is by learning that discrete mathematics, but she would call me out as a liar if I said, if you learn discrete mathematics, then you'll find a good job. And suppose she learns discrete mathematics, but she doesn't get a good job, then you could again call me out as a liar. So the only time this statement would be false would be when Maria learns discrete math, but the consequence is not that she finds a good job. Let's look at another example. What is the value of the symbol x after the statement, if 2 plus 2 equals 4, then x equals x plus 1, if x equals 0 before this statement is encountered? Okay, so there's our if-then statement. So if 2 plus 2 equals 4, then x is going to be assigned the value of x plus 1. Well, the statement 2 plus 2 equals 4 is always a true statement, right? 2 plus 2 equals 4 is always true. So this is always true. And we're saying that an if-then statement, when the condition happens, the conclusion must follow. Therefore, x is going to be assigned the value of x plus 1. So x will now equal 1 coming out of this if-then statement. While not always true, we also have something called the converse of a statement. The converse of a statement is basically just switching the condition and the conclusion. And I've been using that language. This is called the condition, and this is called the conclusion. So if you switch the condition and the conclusion, you get the converse of that statement. If I am in Paris, then I am in France. Well, the first thing I want to do is I want to identify P and Q. So there's P, I am in Paris, I am in France is the statement Q. And so to write the statement Q then P, I would want to say, okay, well, if I am in France, then I am in Paris, and clearly that's not always going to be a true statement. I could be in France, but I could be in a different state, a city, so this is going to be a false statement right here. I could be in other places within France. I don't have to be in Paris. But if I am in France, then we know that Paris, if I don't know what the shape of Paris, here there's a shape of France, let's just say for fun. And Paris is in here. Therefore, if you are in Paris, you know you're in France, but the opposite or the converse does not necessarily hold true.